Okay, class, good morning. Can you see the slide? Anybody?
Yes.
And okay, good. Okay, so we continue what we did last class. So earlier we did about what is meant by modulation. Then we said there are two types of modulation: frequency modulation, amplitude modulation. Why we need modulation? So that many different communications can occur at the same time at the same place without any interference. Okay, that's why we do modulation. Then now we explore to analog to digital signals. Okay, the FM and the AM signals transmitted, is it in form of analog or digital? So they have to decide. Okay, so FM signal got FM analog, FM digital, but nowadays all go for digital, as I say. Okay, so what is analog signal? The voltage varies, the signal value or the voltage varies continuously with time. That's analog signal. A digital signal is a series of high and low values. Okay, there is a series of high and low voltage values. Okay, that's digital. Okay, so I already told you why digital analog is, although it's superior, but got one big pro issue. What's the issue? It pick up noise. Digital also pick up noise. Analog also pick up noise, but analog noise amplified when do amplification. So noise cannot be removed. That's the biggest problem of analog. Okay, in the future, if the technology is there, that they can found able to remove the noise. Okay, then I think it's not going to be digital world anymore. It's going to be like an analog world. Okay, but currently we don't have technology to remove the noise for analog. So should know what is meant by noise. It's an unwanted random power. Okay. Noises caused by the thermal vibration of an atom produces a EM radiation. You know, Maxwell said when an atom vibrates, it accelerates. And when a charged particle accelerates, what happens? EM radiation produced. The EM radiation go and interfere with the signal. So it become that become noise. Attenuation, reduction in the signal power, same like damping, but damping go for oscillation. Two different same kind of what do you call act, but different name. Telecommunication we use attenuation. Okay, so digital got lots of advantage. Not only it remove noise, but it can be encrypted. The circuit is reliable, cheaper. Okay, and yeah. Okay, now we're going to convert. We're going to talk about how analog changed to digital. Okay, so you see here on top, the green color is the analog signal. Okay, some let's say opera singer singing, the voltage changing varies continuously. Okay, from the microphone, the sound changed to electrical signal. The electrical voltage changes continuously. Okay, and this signal amplified by the op amp. Op amp amplified this pattern. Okay, so this pattern later will become like a digital output. This is the digital output. So first, the analog will convert to digital. Analog to digital called analog ADC, analog to digital converter. It's in your phone. ADC is in your phone. When you talk, when you pick up a call, when you talk, the first department will receive your sound is your microphone inside your phone. The microphone convert to electrical signal. Then the electrical signal will send to ADC, okay, to convert the electrical signal to digital coding. Okay, digital coding. So ADC in the department. Okay, then you have another department in your phone again, any electronic device, digital to analog converter. This happens when the digital which is reach your phone, the digital signal will convert back to analog, and that analog signal will be like this, and this signal will be sent to the speaker, and speaker will display the sound. Sound will reproduce back. Okay. Yeah. Okay. So analog to digital converters. Analog to digital converter. Analog to digital converter sample at regular interval of time. it pick up some sample from the analog signal. It takes some sample to reproduce the signal later. The sample, how regularly it takes sample, called sampling frequency. Okay, sampling frequency. You see here the red dots are the samples it collected. Okay, after you collect these samples, when you reproduce the signal, it will flatten all the lines. You see the first red dot in between, you don't have any samples, you know, so you just flatten it until you reach another sample, you flatten it. So all will be flattened, produces this analog signal. Actually, the second one also is analog signal recovered from digital. Okay, analog recovered from digital actually. So this is first job, analog to digital converter. The value of sample voltage measured in each sampling converted to digital binary number. Yeah, each samples will be converted to binary. Meaning, let me go to the next slide to explain that. I think better I explain here. Okay, here better. Okay. See, this is the original analog signal. Voltage varies from 8, become 14, become 2, and yeah, voltage changing. So the analog to digital converter takes samples. It takes samples for an interval of 125 microseconds. Okay, this is the period of samples. Okay, so it takes like a sample. So 0 time, the sample it took from the graph is 8 volt from the signal, 8 volt, and yeah, this is how the samples is collected. Okay, so this is what happened in analog to digital converter. Analog takes samples at equal intervals. Okay. Then what happened? This 8 volt, 12 volt will be converted to binary code. This is the binary code. 1000 is 8 volt. Okay. Okay. You should know how 8 volt write in binary code. In your maths, do you learn how to convert numbers to binary code?
Yeah.
A levels, do you learn that?
No. Only
Never.
SPM.
SPM you learn that. Okay, so SPM you have to recall back. How 8 volt change to binary code. Okay. Okay, for example, this is giving me always trouble. Shut down, right?
Hmm?
Okay. Okay. Let's say you got 8 is you call it's decimal, right? Decimal base. How do you convert to binary? Decimal to binary. So how do you do? You just divide by 2. Okay. So 4 times 2 is 8. So balance is 0. So you can put here balance is here is 0. Balance is 0. Okay. So 2 divide 2 times 2 is 4. Balance is 0. Okay. Divide by 2. 1 times 2 is 2. Balance is 0. Then until you get 1. Then divide by 2. Nothing. Yeah. So balance is 1. So you read from the bottom to top. Okay. So the binary code for 8 is 1000. 1000. This in the binary. This is the binary code for 8. Number 8. Normal number 8 we use. Okay. In exam, you should know. They'll ask you to write binary code. Just ask you the number, write binary code. So let's get what is the binary code for 15. You try. So divide by 2. So what is that? 7 times 2, 14. So balance is 1. Divide by 2. 3 times 2, 6. So balance is 1. Divide by 2. 1 times 2. Balance is 1. Divide by 2. 0. Balance is 1. So 15 is 1111 in binary code. Okay. Okay, if you have 4 digits, this is called 4 bits. Okay, this is called 4 bits. Sometimes this digit can written as 8 bits, 8 bits. How do you write in 8 bits? 8 bits, 0, 0, 0, 1, 0, 0, 0. It's 8 bits. Or another 0, sorry. This is 8 bits. Okay, 8 bits. You see, you put another 4 zeros in front. This is 8 bits. Okay, this is 4 bits. Okay, your syllabus, 4 bits. I only ask about 4 bits. You never go for 8 bits, very complex. What's your computer, your current laptop, processor, processor? How many bits is that? How many bits?
64, is it? Or 64?
4 bits. Means what?
Yeah.
Means what? You got 64 digits,
Right.
It means the 8, if the voltage is 8 volt, how your processor going to code it? You're going to code as 0001, but then got a lot of zeros in front. But the total digit will be 64 digits. But you might think, what is the purpose of having lots of digits? We will get to know later. What is meant by bits? If the binary code got 4 digits, it's 4 bits. Your CD, right? Your CD now it's become obsolete already. Okay, old technology. CD, I think is 16 bit. If I'm not mistaken, music 16 bits. If I'm not mistaken. Okay, so learn how to convert decimal to binary. Okay, hope you understand. Okay, now you must know how to convert binary to decimal also. How do you do that? Let's say you have a binary number 1010 binary. Convert to decimal, how much? So how do you do that now? Each digit, first digit times with 2 power of 0. Second digit times with 2 power of 1. Third digit 2 power of 2. Fourth digit 2 power of 3. So put all the values. 0 times 1 is 0. 1 times 2 is 2. 0 times 2 power of 2 is 0. 1 times 2 power of 3 is what? 8. So it's altogether 10. So it's 10. Decimal is 10. 1010 in binary, decimal is 10. That's how you calculate. Okay. Let's say 1100 binary. What is in decimal? So the same thing. 2 power of 0, 2 power of 1 times with 2 power of 2, 2 power of 3. So 8 plus what? 4 plus 0, 0. So it's 12. So 1100 is actually 12. Okay. Any questions? So you have to know decimal change to binary, binary change to decimal. Okay, go back. Okay, so now sampling has been done. Now this sample we converted to binary code. So 8 the divide by 2, use that method I told you, should be 1000. 12 1100. 14 1110. So you get all binary codes here. This binary code is actually the digital signal. This is your digital signal. Okay, this is digital signal. This is original analog. We already digitalized the analog. Okay, the analog signal has been digitalized. This is what computer understands. Your processor understands only digital signals, 1010. Okay, and these signals, right? This binary, these digital signals will be sent to the modulator in your phone. When you use phone, when you talk, you get this analog signal. You got analog signal, and then analog signal lah. After pass the microphone, it forms electrical signal like this. Then this electrical signal sent to the ADC, analog to digital converter. The digital converter take the samples and it change to binary code. It happens in your phone. And this binary code will send to another department where modulator happen. This binary code will be modulated with the radio wave or microwave in your phone. I think microwave in your phone, modulated. So you know what is modulation. How it going to be modulated? So let's say all the code will be arranged. Someone speak hello, the singer say hello, so the analog signal change hello like this. Okay, so all change to a sample has been collected. So 110001. So all the binary code will be arranged in one row. So this first number will be on top, 1100 something like that. Then this digital signal will be modulated with the carrier wave. So carrier wave, maybe if you modulate here in terms of FM, what happened? The carrier wave, which is normally maybe 500, let's say kilohertz. Okay, then first is one volt. Okay, maybe this as a maybe 50 kilohertz per volt. Okay, per volt. So what happened? This frequency going to change to, for one, it changed to 550 kilohertz. Another one changed to 550 kilohertz. Zero changed to normal 500 back, normal 500. Then another zero become 500 again, 500 again. Then one 550, 550, zero. This is how modulation done. Okay, so FM modulation, frequency modulation. This signal later will send out from your phone. Your phone aerial will send that signal. Okay, to where? To the tower. Maybe your DG or Maxis will get the signal, and this signal will transmit it to your friend phone. Go to the friend phone. Your friend will receive this modulated radio signal. When you receive that signal, what happened? In the first department you're going to face is the digital to analog converter, DAC. Okay, here this wave which reaches your friend's phone will be demodulated. Retrieve back this digital code. Okay, this 551, 500, 500. So it's 000. So the digital code will be retrieved by your friend's phone. Okay. So when this digital reaches friend's phone, then what will happen? That's what we're going to discuss. And what will happen? So this which reaches your friend's phone. Okay. So before we go to that, I need to tell you something. This part. You see, you see the sample it takes, right? The sample it takes 8 volt got code. What is the voltage here maximum? 16 volt, right? 16 volt. So 16 volt, 4 bits, 4 bits only can give for 16 volt. Okay, 4 bits. So 4 bits, the amount of numbers you have in 4 bits is how much? How many numbers? How many different kind of numbers you have in 4 bits? I mean, from the beginning, 0, 0, 0, 0 up to 1, 1, 1, 1. How many variety you have? How many variety? 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1. You know the binary code? Up to 1, 1, 1. How many you have?
15.
16.
16.
Yeah. You see the top here, how much? This is 15, right?
0, 0. Yes.
1, 1, 1, 1 is 15, right?
Plus 0 as a one number.
Plus this on top here, this is another one. Altogether, you have 16 variation. Okay, you have 16 codes. Okay, so now the signal you want to do binary code, you want to change to digital. Let's say the signal got maximum 16 volt. So how many volt will get one code? 1 volt, right? Each 1 volt will get one code, because 16 volt divided by 16 is 1 volt. That means every 1 volt will have a code. Okay, 0 to 1. If the voltage level is 0 to 1 in between, it will code it as 0 0 0 0. Okay, 1 to 2, it will code it as 0 0 0 1. So it only have 16 codes can give. 4 bits only can give how many codes? Only have 16 codes. 16 energy levels. Okay, so yeah. So what happened? Here the signal is 8 volt. So 8 volt, it gives 1000. If the signal is 14.3, do it as a code. Can you give a code for 14.3, specifically for 14.3? You can't, right? So the code is only for 14 and 15 only. 14 and 15 only. So the code you're going to give for 14.3 would be sampled at 14 volt. It will sample at 14 volt. Okay, it go down, drop down. Okay, if the sample they took is 3.8 volt, it's going to be sampled as 3 volt only. You're going to bring down as 3. Okay, because 3.8 we don't have code to give. So always round down. If you got 3.9 volt, analog got 3.9 volt, and do digitalization, you're going to drop to 3 volt. Why? Because 3.9 we don't have code to give. We don't have a binary code to give. The binary code we have is only limited 16 and 16 volt maximum. So each 1 volt get one code. So that's how you get sampling. The real exam, they'll give this analog code like this. When you take sample, if it's 14.5, you take it as 14. 14.9, you take it as 14 also. Okay, this is good or bad? This is good or bad?
Bad.
Bad, right? It's bad. This is where the photocopying lah. You see, photocopy slightly wrongly. The opera singer give a pitch of 14.8, but the digital going to record it as 14. But I tell you nowadays this photocopy is so perfect. Now they use not 4-bit, they use 64 bits. 64 bits. 64 bits. I don't want to go for 64. You go for 8 bits. 8 bits. How many level is at? It has 8 bits. 8 bits. It was recorded 8 bits. 8 bits. It's found to be so 1 1 1 1 1 8 8 8 ones lah. You times all 2 power of 0, 2 power of 1 up to 2 power of 7. 2 power of 7. You add all the number. I think you get 256. 256. If I'm not mistaken.
Yeah.
You notice.
56. So that means 256 volts.
It means what?
256 volts or like 256 intervals.
256 codes you can give.
Volts,
yeah. 256 code. 256 or 264. I'm not sure. The next slide is there. 256. Okay.
0 as one number, so
yeah, 25. I think you get 255. I think plus another one, you get 256. 256 or 264. I'm not sure. But definitely the number of levels increases. That means your signal is 16 volt. Now the 16 volt can be divided by how much? 256 levels, So each level will be how much? Very small voltage, right? That means if your sampling is 14.3, we can give one code for 14.3 now. Understand what I mean? Okay. So we can give a code for 14.3 because we got lots of energy levels, 256 codes available. Okay. So what happened? The digitalization become more perfect, more about better photocopying, as I said. Like is exactly looks like the original analog signal. I tell you, current technology is 64 bits. Imagine how small is the, every small number also you can give a code. Okay, so very, very, very perfect nowadays. 64 bits. Maybe in the future we can get under 28 bits. Okay, so where we are. Okay, yeah, so understand this. So round down. Okay, now you see the recovered signal is very grainy, consisting of large steps. Yeah, it can be, yeah, this I tell you later. So now you got the voltage, change to codes, and this code sent to your friend's phone, demodulation happen, and the demodulation happens, and digital to analog converter, DAC, will trace back the graph, will trace back the voltage. Now you see the setback, it flattened all the values. 8 to 12 interval under 25 milliseconds, a microsecond. From 0 to 125 microsecond, it will take it as 8 volt, flatten 8. It's bad, right? It's bad, but roughly get this shape. Let's get this shape. So this is what you listen from your friend. When friend talk, analog signal. When you receive from your phone, also you listen analog signal, but that analog signal is recovered from digital. It's called recovered analog signal. Recovered, the analog signal is recovered from what? From digital signal. This is what we learn, what we hear. Okay, now I tell you, how do you improve this digital, like exactly same as analog? How you can improve it? You can improve it in 2 ways. Okay, first what? Use more bits. I told you just now, use more bits. If you use more bits, you as I said, if you got 12.3, exactly for 12.3 we can have a code. So recovered also going to be 12.3. Okay, so if you use bits, it reduces the height of steps or the width of the steps. Increasing more bits, it decreases the height of steps or width of steps. Height, the height of steps. The height of steps, okay, the height of steps is affected by the bits. You increase the bits, the height of steps can be more smaller. And the width, how do you decrease the width of steps? The width of steps you want to decrease, you do it in a greater sampling frequency. Increase the sampling frequency. You take more samples. Don't take one sample at 125 microsecond. Maybe take for every 10 microsecond, take samples. Let's say you take 0 to 125, you take another 5 samples in between. Instead, one full step, it's going to be 5 small steps. It'll be 5 small steps, like this. It gets smaller. You can take the shape of this part nicely. But today I tell you the steps are so small until you can't differentiate it. You can't differentiate it. You can't differentiate it because the bits are already went to 64 bits, very big, and the sampling frequency also quite high. So that's why digital looks like, as I said, you compare the live band and your CD, not much of a difference. You are happy with CD, song from CD. The clarity is still good. I think 16 bits. That's why if you have a CD with 8 bits, 16 bits, I think 16 bits will have a better clarity. It will have a better clarity than 16 bits. But nowadays, I think your human hearing can't differentiate 8 bits and 16 bits. Okay, you're not that sensitive enough. Okay, any questions? So in exam, they'll ask, how do you improve digitalization? Have more number of bits. So taking more number of bits, what is the consequence? Having more bits, height of steps can be reduced. More sampling frequency, width of steps can be reduced. So better digitalization. Okay. Okay, so you see 4 bits and 8 bits. Yeah, 8 bits is 256 voltage levels. You can have codes. 4 bits only 16. For your syllabus, they will ask you about 4 bits to calculate. Okay. Okay, now let's talk about sampling frequency. The choice of sampling frequency also determined by the amount of information that can be transmitted. I straight go to the point. Yeah. Okay, go. I show the picture first. Okay, let's say there is a sound like this and like this. Okay. Okay, a signal, analog signal was produced. Okay. Okay. You want to recover this, you want to digitalize the signal. Okay. Okay. Let's say this signal has a variety of frequency. Okay. Point A, point B, point A, B, C, D, E, F. Okay. Yes, a variety because this is in terms of time. So in terms of time, the signal. Okay, it has a variety of frequency. Tell me where's the frequency is highest? Which region is highest? C to D, right? Highest maximum frequency, correct? Because you see the crest to trough, the time is too short. Short time. Short time will lead to greatest frequency, correct? Okay. So when they do digitalization, okay, let's say the digital, they need to have this point. They need to collect this point. They need to collect this point. Okay. Okay. Let's say they digitalize with this timing, A to B. Let's say this is like 5 microseconds. Okay. Let's say C to E also. C to E also, let's say, is 5 microseconds. C to D. C to D. C to D, let's say, is 2 microseconds. Let's say they sample it in such a frequency such that the period is 5 microseconds. Means what? They're going to sample every 5 microseconds. So they'll get the A. Let's say they get a B. In between, they can't take anything because they sample at 5 microseconds. They get A, they get B, they will get C. But do they will get D?
No, they skip.
They skip. They'll get E. Then what will happen to the tracing? A, that digital will be like this. Then B will go down. C, it will go up. But E, it never pick up the D. So the signal will be like this, right?
Yeah, they skip.
So you skip this. You lose this critical information. So what I have to do? So what frequency to sample? What sampling frequency is suitable? The sampling frequency suitable is by taking from this signal, you need to find the shortest crest and trough time. Take the time between that crest and trough, which is the shortest. See, here got crest, you got trough. Time is longer. Take the crest and trough where the time interval is the shortest. Okay, take that time, T1, take that time, then 1 over that T1. That is your sampling frequency. At least, this is the at least. You do, if you have a very high sampling frequency, it's good. But this is the at least. At least. So, crest to trough is what period? Crest to trough is half period, right? Half period. So the sampling frequency is actually twice as the maximum frequency of the analog signal. At least 2 times of the maximum frequency of the signal. Okay, 2 times of the maximum frequency of the. Okay, or in question in the exam they'll ask, go for the crest and trough, which is the shortest time. 1 over that time, you get that sampling frequency. Okay, so that means if you want to send a signal, you want to opera singer sings a signal and its maximum frequency she made, let's say, is 20,000 hertz. That means this audio signal need to be sampled at least how much? To be sampled, what is the sampling frequency? Must be at least 40,000, at least 40,000. So that the crest and trough can be, the nearest crest and trough can be captured.
Wait, why do we need twice?
Yeah.
Why do we need twice?
Because why twice? See, why twice? Okay, let's say this is the highest frequency, C, D, E. Okay, the C to E, the crest to crest. This is the period, correct? So what is the maximum frequency? It's 1 over period, correct?
Yes.
Okay. The sampling frequency, okay, how do you get the sampling frequency? 1 over which time? This timing, right?
Oh,
This timing is half period, right?
half period.
Half period. So half period. Half period is what? 2 over T, right? 2 over T, right? So 1 over T is F max. So 2 over T is how many max? 2 F max, right? So the sampling frequency must be how much? At least 2 times of the maximum frequency. Good idea. Any questions, guys? Okay. Remember, if a signal got high frequency, low frequency, the sampling frequency must be at least 2 times of the maximum frequency of the signal. Okay. That's what explained here. It's like the choice of sampling frequency determines the amount of information that can be transmitted. The greater the sampling frequency is more faithful reproduction. So they found that the sampling frequency must be at least 2F. Okay. For good quality reproduction music, the higher audible frequency is 20 kilohertz. So currently, our telecommunication side, they're sampling at 44.4 kilohertz, more than 2 times. They can reproduce the music more accurately. Okay, they never lose any critical points. Okay, so that the variation can be detected. And you know your human voice, this is something important. You can sense up to 20 kilohertz. Your hearing can hear up to 20 kilohertz. But when you make a sound, right, like a opera singer, the pitch a human can make is up to from 90 to 1,200 hertz. So when your friend make a phone call, what is the sampling frequency the phone must do? Must have. So 2 times of 1,200, so 2,400. Okay, but your telephone system now is sampling at 8 kilohertz, quite high, 8 kilohertz. So telephone, at least 2 times is enough, 2.4, 2,400 hertz. So the highest frequency transmitted receiver is 3.4 kilohertz telephone system. The sampling frequency is 8 kilohertz, very high. Okay. Okay. So this is how you find the selecting the sampling frequency. The sampling frequency, minimum sampling frequency you can take is at least 2 times of the F max. Okay, 2 times of the F max. Okay, real exam, just look at the signal, check from the crest and trough which is the closest. Just take the time. Just take that time. The sampling frequency is just 1 over time. Okay, 1 over time, you get that sampling frequency. Okay, just take the crest to trough, the shortest time. 1 over T, you get that sampling frequency. Okay. Any questions, guys? No questions, Okay. Okay, so that's all about digital. But let's do one question. Okay. One example of analog digital. Let's read the question. Analog signal is sampled at a frequency of 5 kilohertz. This is the sampling frequency. Each sample is converted into 4 bit. Or it's 4 bit. So got 16 energy levels, 16 codes, and transmitted as a digital signal. Yeah. Shows part of the digital signal. 10.1 shows part of the signal, digital signal. So this is digital signal. Okay. Okay. I forgot to say something. Yeah. You see, the 4 bits, right? The first digit on the left, is considered as the most significant bit. Okay. Most significant. In exam, there is one past year exam they ask, which is, please underline which is the most significant bit. Okay. You must go to the first digit on the left. Why it's more significant? Because it carries the greatest voltage, right? 2 times, it's times with 2 power of 3 watt. That has more significant bit. Remember, more significant bit, the first digit on the left. Okay, now this is the binary code given. So it shows part of digital signal. The digital signal transmitted is finally converted into analog signal. On the axis in 10.2, sketch the graph to show the variation of time t of the final analog signal. Okay, so can you draw this analog signal? This digital. Can you draw the analog signal recovered from the digital? So how do you do that? So you use the binary coding. 0010. How many volt? Binary. 2. So you draw here 2. But what is the sampling frequency? Sampling frequency is 5 kilohertz. 5 kilohertz. What is the period time? So period is what? 1/5000. So how much you get? You get 0.2 millisecond. I think you get 0.2 millisecond. So the first code is 2, so it's going to be 2 volt up to 0.2 millisecond. Then only change. Next is how much? 5 volt. So the code will go up to 5 and flatten to another 0.2 milliseconds. Then after that, this is 8 plus how much? 8 plus 10, is it? 10. 10, so you go up to 10 and trace it. And so on. So you see the code, you trace it. This is the analog. This is actually analog. Analog recovered from digital. Okay. Any questions? No questions. It suggests 2 ways in which reproduction of the original analog signal could be improved. The standard 2 answer. Sample more frequently, increase the sampling frequency, use a greater number of bits. But you can add here more. Increase the sampling frequency, therefore, width of the steps can be reduced. Use greater number of bits so that height of the steps can be reduced. Add that. Okay. That's all analog to digital converting.
Yes. Do we need to have higher voltage or more intervals between voltage? Actually,
Higher voltage. What do you mean by higher voltage?
like for example, if 1 bit is 0 to 1 voltage, and if it's 2, for example, let's say my max is 4 volts. Is it better for me to have a sampling signal of 8 volts or 4 volts but more intervals like 3.5, 3.2?
No, this 4 volts is from the original signal one. You cannot control it one. This 4 volts is from the original signal, right? The original signal is made by someone, right?
Oh,
So,
okay.
so that voltage you cannot control it.
Unless there's an amplifier.
Unless you do amplification, you can increase it. Or whatever it is. If you're increasing to a significant voltage, the digitalization depends to how many levels you have available. How many levels you can break. That where digital, how accurate is the digitalization happen. So you need to have more levels. That means you need to have more bits. If you have more bits, with more bits, you can have a better digitalization. Okay. Any questions?
Teacher, another thing, if my sampling signal has a lower bits than the analog signal, that means that it will be capped at a maximum voltage value if it goes over it.
Yeah, correct. Let's say the signal maximum is let's say is 30, what I say, 32 volt, 32 volt. So the 32 volt will be given the maximum code 1111. Okay. So the 32 volt you divide by 16, what do you get? 2 volt. So every 2 volt will get one code. 2 volt will get a code 0001. 4 volt will get a code 0010. 3 volt, 1 volt don't have code. That's your question.
Yes.
Okay, but your exam, to make it easier, they only give up to 16 volt. That means every 1 volt is one code. Okay. Okay, guys. So that's about today's class. So we're done with the digitalization. Another 1 hour, we finish the syllabus already. Another 1 hour. So tomorrow we'll be finishing the syllabus 1 hour. Then another 1 hour we do the questions. We do the questions. You can go to the what do you call? Yeah, the telecommunication questions. Questions here. You got plenty of questions. Yeah, so this is because June 07 the telecommunication started. So June 07 to up to what? June 7 to up to 11, about 4 to 5 years question. You go through this, you go through this question, you will see the question is repeated. The same question, the repeated. You see the AM, and a few years back, still get the same style of questioning. Okay, AM, and the drawing part again starts, and so on. So the question is rigid. So worth studying. You definitely have one telecommunication question for your paper 4. So worth studying. Okay. So we'll discuss this later. Okay. So tomorrow what we're going to do is we're going to discuss where do we put the amplifier. Okay. Where do we help the Mexican company, the telecommunication company, to save money? Because when the signal is transmitted, it experiences attenuation. But where do you need to put the amplifier? What is the maximum distance you can put the amplifier so that we have a minimum number of amplifiers, so save costs? Okay, you can't put too long. If you put too long, you lose signal. You can't put too short. You can put too short if you want, but costly. So they want to see the maximum distance, limited amplifier, at the same time never lose the signal. It's what we're going to calculate tomorrow. Okay. Any questions? No questions, Okay, so see you then tomorrow. Last class. I mean the last class for the syllabus, and finish the syllabus. Okay, thanks.